Hello everyone, welcome back to my channel. My name is Dr. Yogita Bisht, and in today's video we will study molality and mole fractions, and we will solve some numerical also based on this. This video is in continuation from my series of mole concept, where we have studied about the what is mole and how to calculate the number of moles. There are 4 different ways. I have explained those in videos. And then we studied about the molarity and normality, what is the difference between these two, which one is preferred. And now we have moved to the another form of measuring the concentration of the solution, that is the molality and the mole fraction. If you haven't watched those video, I will provide the link for this video. I would recommend to watch at least once these videos, because you will get to know how to calculate the number of moles. That is the core concept that you are going to use in all the concentration measurement numericals. All right, so let's just start with this. Okay, so first I'll start with molality. Molality, as you all know, it is represented by small m, and I will also explain the difference between the molarity and the molality, and why there was a need of the molality, where there was already some terms like molarity and the normality to measure the concentration of the solution. So let's just begin with the basic formula. What is molality? Molality is basically given by number of moles of the solute divided by mass. Please remember, it's mass, okay, not the volume. Mass of the solvent in kg. This is the formula. Okay, if I compare it with molarity, molarity had the formula of molarity represented by capital M. This is the first difference. This is represented by small m. This is represented by capital M. This was given by number of moles of the solute divided by volume of the solution in liter. So this was the formula for the molarity. So you can clearly see the difference. Here we are using the solute, but in molality we use the term solvent, and in molarity we use the term solution, and here we talk about the mass of the solvent, and here we talk about the volume of the solution, and that make all the difference. Okay, how? For that we need to understand the procedure to prepare a molar solution and a molar solution. Okay, so first we will study that, and that will clear all your doubt. Okay, so let's say prepare 1 molar NaOH solution in water, and prepare 1 molar NaOH solution. Okay, so how we are going to do that? Let's say we are preparing it in a 1 liter standard flask. So this is our 1 liter standard flask. So you do know the basic procedure how to do that. What we are going to do is, first we are going to find out how much weight of the NaOH is required to prepare the 1 molar solution in 1 liter. So we can easily do that. We know that the molar mass of NaOH is 40 grams per mole. So to prepare 1 molar solution of NaOH in 1 liter, NaOH required is, we can easily calculate that. Why? Because we have the formula molarity, that is 1 number of moles of the solute. Number of moles, that is the given mass, divided by molar mass of the NaOH is 40. I'm writing it in, not writing in detail because I have already explained this in previous videos. Okay, multiplied by, here we have the volume, that is 1 liter. Okay, so from this we can find out that the given mass is 40 gram. That means to prepare 1 molar solution of the NaOH in 1 liter solution, we have to add 40 grams of the NaOH solution. Alright, so here our NaOH is the solute and water is our solvent. And the combination of these two will be the solution. So the total volume need to be 1 liter solution. So what we are going to do is, first we are going to weigh, this is NaOH, weigh 40 grams of NaOH. We have to weigh that, okay? And then what we have to do is, we have to add this in the standard flask, okay? And to this we are going to add, this is NaOH, we have added NaOH, and to this we are going to initially add little bit of water, okay? A bit of water to this, and then we are going to shake it, mix it properly, and then we are going to fill rest of the water. We don't know exact water we are going to add, we just need to fill it till this mark, and this will give us the total solution. Okay, so what we did is, we first added NaOH to the small amount of water and then mix it properly and then add rest of the water. This is how we prepare the molar solution. Now to prepare the 1 molar solution, again if you do the calculation comes out to be the same, that is the given mass would remain the same, that is, it is let's say we are saying that we are adding 40 grams of NaOH in 1000 grams or 1 kg of water. Okay, again the solute is NaOH and the solvent is water, but in this case the procedure would be the different. Okay, first we are going to weigh 40 grams of NaOH, okay, and in the next step what we are going to do is, again we are going to take 1 liter standard flask, but this time what we are going to do is, we are going to add either 40 gram of NaOH first, okay, 40 grams NaOH first, and then we are going to measure exactly 1 kg of water. 1 kg of water to this flask. Now this time it may or may not coincide with the exact mark, 1 liter mark. It may or may not, okay, but it doesn't matter. In this case we fill the water till this mark, whereas here we just simply calculate how much water we required, how much NaOH we required, and we just mix them quickly. Okay, you must be wondering like how to add 1 liter of the solution. So here for that what you have to do is, you have to check density of water, okay, and density of water vary with the temperature. Okay, so at that particular time when we are doing this experiment, you have to check the density, what is the temperature, what is the density, and then using that you have to calculate the volume and the mass of the water that you are going to add. Okay, so I'll explain that also in detail, like how from density how to calculate the exact mass with the help of the numerical, but right now just try to understand the procedure. Here we don't know the exact volume of the water, we just add it to this mark, whereas here we exactly know how much water we are adding to the 40 grams of the NaOH, and here we talk about this weight or the mass of the solvent. Okay, I hope this is clear, the difference between the procedure of the of making molar solution and the molar solution. All right, okay, so before moving to numerical part, I would like to explain why molality was needed. Right, because you know molarity, normality, mole fraction, mass fraction, all these terms are used to measure the concentration of the solution. So we already had molarity. Then why molality was needed? What was the need for that? Okay. So for that you need to remember one thing, that molality is not temperature dependent, whereas molarity is temperature dependent. I'm writing this up and you need to remember it for the practical use, because molarity and normality are dependent on the temperature and pressure, whereas molality does not depend on temperature and pressure. Okay, this is something that you need to remember. I'll show you how. Okay, let's say prepare again 1 molar NaOH solution at different temperature. Okay, so first you are start making it again in the same 1 liter standard flask. Okay, this is NaOH plus water, but you are making it at, let's say, 50 degrees Celsius. Okay, in the another case, what you are doing is you are reducing the temperature. Okay, let's say again you are making the same solution. This is standard flask. Again the volume is, this standard flask has the same size. This time this has again NaOH plus water. Okay, this is the mark. This mark and the volume of the solution will coincide. Okay, now we are, when you are preparing it at for the same solution at, let's say, little bit lower temperature, let's say 5 degrees Celsius. Okay, then you will realize that the volume of this total solution has been reduced. Okay, maybe a bit, which is almost negligible, but it will not coincide with the exact volume. Okay, so that is why the volume would be little bit lesser. So in this case, volume of solution is same as 1 liter, as up to the mark. This mark represent 1 liter solution, but in this case the volume of solution will be less than 1 liter. Now let's take the third case. In third case, you are taking the same standard flask. Okay, this is again the standard flask. Okay, you are preparing same NaOH plus water, but this time let's just raise the temperature to 90 degrees Celsius. So of course you know that with rise in temperature the volume slightly increases. Okay, so this time volume of solution will be more than 1 liter. Okay, so you can see with change in temperature the volume is changing, and we know that molarity is inversely proportional to the volume, right? So what is going to happen, the molarity is not going to remain the same. Here molarity is 1. Okay, in this case molarity will be little bit higher, and the other case, so in both the cases the molarity will be little bit different. Okay, since in case of water you will say okay, it hardly changes. If you check the data, you will realize the temperature, with temperature the volume or the density doesn't change that much. Okay, but in bigger experiment where the precision is required, these factors should be taken into account, or in this case we have taken water, so you don't see much difference. But when we take some other solvent, like let's say alcohol or maybe some other oil or something like that, then in that case you will realize that it changes a lot with the temperature. Okay, so that is why the molarity sometimes is not preferred, or sometimes in your lab you don't keep the solution for longer time period because the temperature will vary, right? So the volume, the molar solution that you prepared a week or month before, it will not remain the same after a month. Okay, there will be the change in temperature, there will be change in the volume, that is going to affect the molarity. Okay, whereas in case of molality, in case of molality, it will remain the same. You are taking 1 liter standard flask, right? To this you are adding NaOH plus 1 kg of water. So every time you are adding just 1 kg of water, so this is not changing with the temperature. Okay, so that is why irrespective of the temperature, the molality is going to remain the same. That is why in certain experiment molality is preferred over the molarity or the normality. Wherever there is a mention of the volume, you can just mention, okay, it may vary with the temperature and pressure, that is why we will not prefer it. Okay, this is very important to know from the experiment or the practical point of view. All right, so this was about why molality is preferred sometime. Okay, now we are starting with the numericals. Okay, so first we are starting with numerical, easy numerical. Okay, so it says calculate the, I'm just writing small m, molality of a solution prepared by dissolving 18 gram of glucose. Glucose is C6H12O6 in 180 gram of water. Okay, and molar mass of glucose is given as 180 grams per mole. Okay, so you have to calculate the molality. It's very straightforward and simple question. So we know that molality has a formula of number of moles of solute divided by mass of solvent. So in this case, solute is glucose and solvent is water. Okay, this has to be in kg. All right, so first we have to find the number of moles of solute. So number of moles of glucose, this is given mass divided by molar mass. So given mass is 18 gram and the molar mass is 180 grams per mole. So this is 0.1 mole. Okay, and mass of the solvent is already been given, it is 180 grams. So we have to convert into kg. Mass of water is 180 grams, which is nothing but 180 divided by 1000, that is 0.18 kg. So we can simply put it in the formula. So the molality would be 0.1 divided by 0.18, that is 0.556 molal. All right, so I hope this was easy to understand. Now let's just try some other numerical. Okay, so it says how many grams of glucose should be dissolved in 250 grams of water to make 1 molar solution. So this is also very easy and straightforward question. We need to find out how many grams we need to dissolve. So we know that molal is number of moles of glucose divided by mass of water in kg. Okay, so this can be written as mass, number of moles of glucose as mass of glucose divided by molar mass of glucose and multiplied by mass of water in kg. Okay, so now we can put all the values. So this is going to give you 1. You need to find out mass of glucose divided by molar mass of the glucose is 180 multiplied by mass of the water in kg. It is in 250 grams, so we have to convert it into kg. So this will be 0.25 kg. So therefore mass of glucose will be 1 into 180 into 0.25, which is 45 gram. So this much glucose I need to add to 250 gram of water to make a 1 molar solution. Alright. So let's just move to another numerical before we move to the mole fraction concept. It says 15 gram of H2SO4 was dissolved in 575 ml of water. Okay, at 80 degrees Celsius. The density of water at 80 degrees Celsius is 0.997 gram per ml. Calculate molality of the solution. This is the question. Okay, so it may look little bit difficult to answer, but this is very easy, same as that the previous 2 questions that we have done. Okay, so first you need to find out what is a solute and what is a solvent here. So solute here is H2SO4 and solvent here is water. So you must be wondering, H2SO4 is also liquid, how come it is a solute? So solute need not to be a solid thing. Anything which is present in a little bit lesser amount, it will normally consider as a solute, and the other one which is present in the larger amount is considered as the solvent. Alright, to find out the molality, we need to find out the number of moles of solute, right? So first we need to find the number of moles of H2SO4. So that is given by given mass over molar mass. So given mass of H2SO4 in this case is 15 divided by molar mass of H2SO4 is 98.08. This will be provided to you in any question, so you need not to mug it up. So this will be 0.153 moles. These are the number of moles of the H2SO4. Now for the molality, we also need to know the mass of the water at 80 degrees Celsius. What is mass of this? Okay, it is not being provided to us, but volume is being given. Volume is 575 ml and density is 0.997 gram per ml. So we know the formula for the density. From that we can find the mass of the water. So the density has a formula of mass upon volume, which means mass will be density multiplied by volume. Okay, therefore mass of water in this particular case, this will be 575 multiplied by 0.997 gram. But we need it in kg, right? So we have to divide it by 1000. So this will be 575 multiplied by 0.997 divided by 1000 kg. So this will be the mass of the water. So if you calculate this, you will get it 0.573 kg. This is the mass of the water. So now we can easily calculate the molality. Molality is number of moles of solute divided by mass of solvent in kg. So this will be 0.153 divided by 0.573. So we will get 0.27 mole. Okay, alright. So this was about the molality. Okay, now we are moving to the next concept, that is mole fraction. Okay, this is represented by X or Xi. Okay, so what is a mole fraction? Mole fraction, basically it is also another way of representing the concentration, but in your solution, let's say you have A component, B component, C component, or maybe only two components. So how to express the concentration of the each component? We need a term for that. So normally we use mole fraction, sometimes mass fraction as well, to represent the concentration of the each and every term. So you can write it down. It is a way of describing concentration of each component of a solution. Okay, and the formula for this is, let's say we want to find the concentration of a component 1, okay, or the mole fraction of component 1. So this will be given as number of moles of component 1. Okay, number of moles of component 1 divided by total number of moles. Okay, so I'll give you a simple example. Let's say in a solution we have component A and component B. Okay, let's say component A is H2SO4 and component B is water. Okay, so in this case, the mole fraction of component A will be given as number of moles of component A divided by number of moles of component A plus number of moles of component B. Similarly, mole fraction of component B will be given by number of moles of component B divided by number of moles of component A plus number of moles of component B. We can use the same formula for multi-component system also. There can be 3 system, 4 component, 5 component, it doesn't matter. The formula is going to remain the same. Okay. All right. So you can see basically it represents the fraction. So that is why if this system consists of only 2 components, that means the fraction of, that is the mole fraction of component 1 plus mole fraction of component 2 should give the answer 1. Okay, so this also a very important equation you can say to calculate the numericals. Alright, and you already know how to calculate the number of moles from the given data. If you don't know, you can watch my previous video. So number of moles calculations are very, very important to know if you want to calculate the concentration of any solution. Alright, so things will become a bit easier to understand with the help of a numerical. Let's just start with a numerical. Alright, so one of the numerical says a solution is made by mixing 5 gram urea. Its molar mass is given as 60 grams per mole. 34 gram of water. We already know the molar mass for this is 18. And 46 gram of ethanol. It is a typical question. Normally this is the component ratio that is being provided. Its molar mass is 46 grams per mole. Find the mole fraction of urea. This is also a pretty straightforward question. So what we have to do is first write down the formula. So mole fraction of urea will be given by number of moles of urea divided by number of moles of urea plus number of moles of water plus number of moles of ethanol. So we just need to find the number of moles of urea, water and ethanol, and we can easily calculate this. So first, number of moles of urea, this will be given as given mass divided by molar mass. So this will be 5 divided by 60, that is 0.083 moles. Okay, number of moles of water, this will be, number of moles is given as 34 divided by 18, so this is 1.889 moles. Then we have number of moles of ethanol. Number of moles of ethanol, the given mass for the ethanol is 46 and its molar mass is also 46, so this will be just 1 mole. Okay, so we can put this in the formula. The mole fraction for urea will be 0.083 divided by 0.083 plus 1.889 plus 1. So this will be 0.028 without any unit. Please do remember there is no unit for mole fraction. Why? Because in the numerator also we have number of moles, in denominator also we have number of moles, so the unit cancel out. It is basically represent fraction, and you already know the fraction doesn't have a unit, so it's a unitless quantity. Alright, so I hope this was easy to understand. Now let's just move to a little bit of the difficult question. Alright, so there we will combine all the knowledge to find out both molality as well as the mole fraction. Okay, so this will be the last question of the video. It says a solution contain 20.0% weight by weight. I'll explain what does it represent. Weight by weight. Ethanol with the molar mass. Here the molar mass, exact molar mass is given 46.07 grams per mole. Okay, in water. So it's just a two component system. Calculate number 1 molality of the solution, number 2 mole fraction of the ethanol. Okay, and they have mentioned use 100 gram of solution. This was important, otherwise we should have assumed that it is 100 gram of the solution. Okay, so first let me explain you what does 20.0% weight by weight represent. It represents what is the weight of the solute versus solvent or solvent ratio. Okay, weight by weight means 20% weight by weight of in a 100 gram solution. It means it contains 20 grams ethanol plus rest water. This is making a total solution of 100 grams. Okay, so mass of water in this solution is 100 minus 20, that is 80 grams. Okay, normally in question they don't give this 100 gram solution, you have to assume it. Okay, 20 weight by weight percent, that means it is the solute and rest is the solvent. Okay, so now we already know the mass of the solute and the mass of the solvent. Molar mass we already know. We can easily calculate the mole fraction and the molality. Okay, so let's just do that. First we are going to calculate the number of moles of ethanol. Okay, so number of moles of this ethanol will be given as given mass divided by molar mass. I am rewriting the formula again and again so that you can remember it by heart. Okay, so the given mass for this this particular case is the mass of the ethanol is 20 and the molar mass is 46.07. Okay, so this will give you the number of moles of solute, that is ethanol, is 0.4340 moles. Okay, and for molality, first we are calculating the molality. So mass of solvent, which is in this case water, is 80 grams, or you can also say 80 divided by 1000, that is 0.08 kg. Okay, so formula for molality is number of moles of solute. It is a good habit to rewrite all the formula. Okay, number of moles of solute, in this case ethanol, divided by mass of solvent in kg. So we have both the values. We can just put it here and find the answer. So this is 0.4340 divided by 0.08. Okay. So the answer is 5.425 molar. This is the answer. Okay. And the next question was find the mole fraction. Okay. So for mole fraction of ethanol, the formula we already know. Number of moles of ethanol divided by number of moles of ethanol plus number of moles of water. Okay. So we have already calculated the number of moles of ethanol. First we need to find out the number of moles of water. So this will be, given mass of water is 80 divided by 18. So this will be approx 4.443. Okay, so this is the number of moles of water. So now we can just put it in the formula. The mole fraction of ethanol would be 0.4340 divided by 0.4340 plus number of moles of water 4.443. So this will be around 0.089. This is the mole fraction of ethanol. You can keep it like this, or you can convert it into percentage also, which is nothing but just by multiplying by 100, 8.9%. Alright, so this is the maximum type of application of the molality and the mole fraction question you can get in exam. Okay, in future I'll take more such complex questions, but for today this is enough. Alright, so thank you so much for watching today's video, and if you have any doubt you can comment below, and if you want to study some other topic that I have not covered yet, you can also mention that. Okay, thank you so much.